We're going to focus just on the quadratic family today. The parent function is y equals x squared. In order to show you what the graph looks like, which as you should know is a parabola, I'm going to make a table of values so that you can kind of see what's going on. So when we make a table of values, our standard numbers are always going to be from -2 to +2. Those numbers could possibly change if there are transformations on the graph, but for the standard parent function, that's what we're always going to use. So if I plug in -2 into the parent function, that would be -2 squared. A negative times itself is always going to turn positive, so this would end up being 4. -1 squared would end up being 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. You'll notice that it's symmetric. So you have your middle right here where I'm putting an orange star, and then you'll notice that you have both of the y values are 1s and both of the both of the y values are 4s as you work your way out. And that will always happen with a parabola because they are symmetric on both sides. This middle point that I put the star by has a special name. It's called the vertex. And depending on if the parabola is facing up or facing down, it's either going to be your highest or your lowest point. So I'm going to plot these points now. So I have -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And then if I connect these dots, that's what creates the parabola or the parent graph for the quadratic family. We've talked a little bit about domain, range, and end behavior. The domain of a parabola is all real numbers because it's going to constantly be going farther and farther to the left and to the right. So it would eventually cover all the x values. The range is not all real numbers because you'll notice that it does have a highest and a lowest, or either has a highest or a lowest point. In our picture here, it has a lowest point, and that's this point right here. That's that vertex that we were talking about. So we're going to have to do an inequality. Range is talking about y values, so I'm going to use y. And in this particular picture, since the vertex is my low point, that means that all my y values are going to be greater than or equal to whatever that y value is, which in this problem is 0, and I'm talking about this 0 right here. For the end behavior, we're talking about as x goes to the right, so towards infinity, and as x goes to -infinity, or towards the left. So as x goes to the right, my y values are going towards infinity because they're going up. As x goes to the left, towards -infinity, my y values are also going up. So both my y values are going towards infinity, and then I have one of each for my x values. Now this last thing that we need to talk about is called the axis of symmetry. I mentioned that parabolas are symmetric, meaning if I folded it in half, it would fall right on top of itself. And where you would fold it in half so that would happen is called your axis of symmetry. So I'm going to draw a red line right through the middle of the parabola. So if you imagine that I took this parabola and I folded it over this red line, both of those sides should fall exactly on top of each other. The axis of symmetry will always be an equation. So I'm going to put a star here because you can't just write a number. It has to be an equation. It will always be x equals, and then it will be the x value of your vertex. So here the vertex is 0, 0. And the axis of symmetry would be x equals 0. X equals lines are vertical lines. So really what you're doing is you're trying to find what number, at what x value would it cut the parabola exactly in half. And if I put this at x equals 0, it would cut this blue parabola exactly in half. We're going to find the indicated information for each graph, and then we're going to compare it to the parent function. And that's really what this unit is all about, is comparing all of these graphs back to their family of functions. All right, so for the first one, what I like to do first is find the vertex of the graph. It helps me to be able to see what happened. So I'm looking for the lowest point, or you could also think of it as the turning point. So if you follow this parabola, if you go from left to right here, it's going down, and once you get to the vertex, then it starts going up. So it's where the turning point is. So normally the vertex of the parent function is at 0, 0. So where I just put that other blue dot. So now if you compare where the vertices are, you can get a better idea for how it got transformed. So I noticed that it went 1, 2, 3, 4 to the left, and then up 3. Now it's asking me for the equation. Remember that we have kind of our general form. Since we're talking about just quadratics, I'll actually put the square on there. So there's three numbers we need to worry about. The A number would tell us if the parabola was stretched or if it was shrunk. It would also tell us if it was reflected. And if I'm looking at my graph here, I notice that it doesn't look like any of those things have happened. It's facing up, so I know it's not reflected. And the reason I know that my A value has not changed, we're going to check it kind of like we do with slope. So if we start at this blue dot, the vertex right here, what we're going to do to check to see what the A value is we're always going to go 1 to the right. So we're going to go 1 box to the right, and then your A value will always be however many boxes it takes for you to get to the graph. So always go 1 box to the right, and then it only took me 1 box to get back to the graph. So that means my A value is 1. And that's the same as it is for the parent graph. So that's not a difference. There's no transformation for A. All right, so my equation, I have everything that I need. My left 4 is telling me my H value, and my up 3 tells me my K value. So my equation is going to look like this. I don't have an A value that's different, so I just need my parentheses. Since I'm going left, I would have x plus 4, because it's the opposite of what it looks like. And then I would go up 3, so plus 3. Now the vertex, you can count it from the graph. It's actually a combination of your translations. So since I went left 4, my vertex is going to be -4. And I went up 3, so my vertex will be +3. My axis of symmetry, remember that's the line that you would draw that goes right through the middle. And I told you that it will always be x equals. And then you can always take the x value of your vertex, which is -4. And if you look at the graph, if you count -1, -2, -3, -4, that's exactly where that line is. The domain and range of a parabola, we need to talk about next. The domain is going to be all real numbers. It's going to keep going to the left and to the right forever and ever. The range is going to be an inequality. Since this parabola is facing up, my y values are going to be greater than or equal to the lowest point. So now I'm looking at my y values, and my lowest y value is 3. And you'll also notice that this 3 shows up here in the vertex, and that is not a coincidence. It means the same thing. The last thing we need to do is end behavior. Remember that you have 2 parts to your end behavior. Once when x goes to the right, once when x goes to the left. And if I look at my parabola, both ends are actually going up. So I know that both of my y values are going to be going towards +infinity. For problem number 2, the first thing I want to do is kind of pick out that vertex. So here's this. And then before we write down our transformations, let's check our A value. So I want to go to the right one, and then I have to go 1 box to get back to the graph. So that's telling me my A value is 1. And then I also notice that my graph is upside down. So what that means is that my A value is negative. So I'm going to write that A is -1. And then when I do my transformations, I'm going to write this, that it was reflected because it's negative and it's upside down. And I don't have a vertical stretch or shrink. I don't have to write that because the number is 1. And then if you look at your vertex, normally your vertex is at 0, 0. So it looks like it went 4 to the right, and then it went down 3. So my equation would be y equals, I have my negative for the reflection. I don't need a number for A because it's already 1. Since I went right 4, I'm going to do the opposite and put x minus 4. And then, down 3 would be negative 3, minus 3. All right, the vertex, like I said before, is a combination of the horizontal and vertical translations, or you can count it from the graph. So the vertex was right 4, down 3, so 4, negative 3. Axis of symmetry is the line that cuts the parabola in half. And if you look here, remember it's always x equals. It goes through the x value of 4, which is the same as the x value of your vertex. Domain and range are going to look really similar to problem 1. Domain is all real numbers. This time the range is going to be y is less than or equal to the y value of negative 3. And that's because the parabola is upside down. So now negative 3 is the highest point and everything else is below. And then last but not least, end behavior. So I have x goes to infinity, x goes to negative infinity. So that covers both when x goes to the right and the left. Both of the ends of the parabola point down. So that means that for both of these, my y value is going towards negative infinity. All right, number 3. So I'd like to identify the vertex. This graph looks a little funny because it goes by halves instead of by ones. So just be really careful. My vertex here is actually 1, 1. Now let's take a look at the a value. So I'm going to go right 1, and then I have to go down 1. So that means my a value is 1, and because it's flipped upside down, it means it's actually negative. So it's going to look a lot like number 2, where we have a negative in front of the parentheses but no number. All right, so transformations that are happening. It is reflected. And it also shifted to the right 1 and up 1. So now my equation is going to look like this. I have my reflection, so that's a negative. Since it's right 1, I'm going to say x minus 1, and then up 1 is plus 1. My vertex is where this blue dot is, so it's at 1, 1. Axis of symmetry is always x equals the x value of our vertex, so x equals 1. Domain is going to be all real numbers, just like the other two. The range is going to be less than or equal to the highest y value, since this is upside down, and my highest y value is 1. End behavior, I need one of each, x equals infinity and x equals negative infinity. And if you look at this graph, since it's facing down, both of my y values are going to be going towards negative infinity. Okay, last example, talking about interpreting these graphs. So the vertex here is at this top point right here. It looks like negative 3, 4. And the next thing we need to talk about is the a value. I can tell right away that the a value is going to be negative since this parabola is facing down. If I go to the right 1 box from my vertex, and then I go down until I meet my graph, do you see that we actually have to go down 2 boxes till we get to the graph? So this tells me that my a value is 2, and it's going to be negative 2 since it's upside down. So there are a lot of transformations happening here. My first transformation is that it's reflected. It's also stretched because 2 is bigger than 1. So this is a vertical stretch. And then if you look at the vertex, normally it's at 0, 0. So it moved left 3, and then it moved up 4. So that makes my equation negative 2, and then I have left 3, so that's going to be x plus 3, and then up 4 would be plus 4. My vertex is going to be the vertex that we figured out at the beginning, negative 3, 4. Axis of symmetry will always be x equals, and it's going to be the x value of my vertex, so x equals negative 3. So that would give me my line that goes exactly through the middle of the parabola. Domain is going to be all real numbers because this would keep getting wider and wider forever. Since this is upside down, my range will be everything less than or equal to my highest point, which is the y value of my vertex, or 4. And then end behavior, I can set up x equals infinity, x equals negative infinity. And then in a parabola, you may notice that this is always going to kind of work out this way. It will always, your y values will always be the same because they're always going to be pointing in the same direction. So since these are both pointing down, that means both of my y values are going to be going towards negative infinity. In this example, we're asked to graph the function x plus 1 squared plus 3. First thing I want to do is talk about the transformation. So I'm going to write that standard general form, the y equals a times x minus h squared plus k. That's our general formula. And what I want to point out are that the transformations are going to be affected by the a value, h, and k. So if you look at our function, we don't have anything in front of our parentheses. So what you can assume is that that number is a 1. And that number is not going to stretch or shrink our graph. It's going to make it the exact same width as the parent function. The other two values, the h and the k, those are telling us about horizontal shift and vertical shift. And in this problem, we have both. So I have a plus 1 here and a plus 3. One thing you need to remember about the horizontal shift is that because we have this negative in our formula, when we look at an actual function, whatever our horizontal shift looks like, the sign, is actually going to be flipped. So this function right here, because I have a plus 1, means that our graph is actually going to be shifted left 1. And then your vertical shift doesn't change sign. So it's left 1, and then it's also going to be shifted up 3. And I want to just very quickly, off to the side, show you why that sign change happens. If I take these transformations and I plug them in, I'm going to ignore the a because this one doesn't have an a value. But if I use our general formula almost, I would have x minus, and then left 1 would be minus 1, and then plus 3 would be up 3. So this double negative here, because I have a negative from the standard form and I have a negative from the left 1, that's why this right here turns into a positive. So I know it seems bizarre that we have to switch the sign, but there is a reason. All right, so now let's get into the actual table. The first thing that we're going to want to do for every single table is we want to identify what the middle point of our table is going to be. And in these problems, the middle point of our table is going to be the vertex. And there's a really easy way to figure out what the vertex is. The vertex, as long as your equation is in this general form, is always going to be hk. So you have to remember to always flip the sign for h. And then k stays as is. So in our problem here, our h value is this plus 1, but we have to flip the sign. So I want this to be negative 1. And then our k value is going to be positive 3. So that will always give you your vertex. And I'm going to go ahead and write that over here, negative 1, 3. Now to fill in the rest of my table, I'm going to continue counting down 2 boxes, and then I'll count up 2 boxes. So if I count down, I would have negative 2, negative 3. And if I counted up, I would go to 0 and 1. Now all I have left to do is figure out the rest of these. We could do these by hand. We could figure it out in our head. It wouldn't be terribly difficult. It would just be a little bit of a time-consuming task. So in the following parts of this video, you're going to see how you can calculate a table of values using a calculator. And if you don't have a calculator that does that, the first video is showing you how you can use Desmos to do that. So I'm going to fill in these numbers, and like I said, in the following parts of this video, you'll be able to see where these numbers came from. So I have 7, 4, the 3 that I already had, and then 4, 7. Now something I want to point out about this table is that you'll notice that the y values are symmetric, and that's not an accident or a coincidence. It will always happen that way when we're talking about the quadratic family. So your vertex is kind of like in the middle, and then if you look here, as you go out a box, the 4s match. As you go out another box, the 7s match, and that pattern would continue if you saw more of these table values. So that's a nice way that you can double check that your values are correct, because if you're not seeing that symmetric pattern, something went wrong. And it's also a nice way to kind of double check that you've picked the right vertex, because as long as your vertex is right here in the middle and everything around it is symmetric, that means you did it right. All right, so I'm going to graph these points now. So -3, 7 would be here, -2, 4, -1, 3, 0, 4, and 1, 7. So I can connect the dots, and that gives me my parabola. When you connect the dots, make sure that you're connecting it in the shape of a U. Don't make it like a corner, like a V shape. All right, for domain, we're talking about how far left and right will this graph go if I went on forever and ever to the left and right. And the answer is it would keep going left and right. So my answer there for domain is all real numbers. For the range, because my parabola is facing up, my y values will go up forever and ever. But they don't go down forever and ever. There's actually a lowest point, which is right here at this vertex. So because it doesn't go forever and ever, I have to use an inequality. And because we're talking about range, I'm going to use y as my variable. And it looks like the lowest point that the y values get is +3. So I know that I'm going to use y and 3. And then because all of the y values are 3 and then everything bigger, so like 3, 4, 5, 6, 7, going on forever and ever, I want all the numbers that are bigger than 3. It's also okay if my y value is exactly 3, so I'm going to use greater than or equal to. My axis of symmetry is always going to be a vertical line, x equals, and then you can find the value that we're going to use by looking at the x value of our vertex. And remember that the axis of symmetry is a vertical line that if you drew it on your graph would cut your parabola exactly in half, so that if you folded the parabola on that axis of symmetry, both sides would fall right on top of each other. And then the last part is end behavior. And what I like to do with end behavior is I like to set it up because I know that I'm going to have one statement when x goes to -infinity and one statement when x goes to +infinity. So when x goes to when x goes to -infinity, what I'm really talking about is as x goes to the left. So I'm going to put a big L here for to the left side. So I'm going to focus here on my left arrow. My left arrow is pointing up. And in order to show that using these symbols, we're going to say that y is going to +infinity. And then when x goes to +infinity, so now I'm talking about the right side of my graph, if I look at the arrow on my graph, it's also pointing up. So that means that my y value in this expression is also going to +infinity. So when we're talking about end behavior, what we're really saying is it's a really fancy way to write as x goes to the left, is my graph going up or down? And as x goes to the right, is my graph going up or down? So I like to think of it that way as I'm writing. And then I just have to remember what means what. So I'm going to make a quick little chart here. So if we're talking about our x's, if I'm saying -infinity, I'm talking about the graph going to the left. If I'm talking about +infinity, I mean that the graph is going to the right. And same thing, if I use that for y, -infinity now means that my graph is going down, and +infinity means that my graph is going up. In order to use Desmos to find a table of values for our function,
we are going to need to use the graphing version of the Desmos online calculator. You can also download the graphing calculator Desmos app for your phone. In order to get there on your computer, you're going to type in www.desmos.com/graphing. When the calculator opens up, you can see the graph on the right, and then on the left side here is where you would either type in functions, or in our case, we're going to put in a table. So to add a table, we're going to press this plus sign that says Add Item, and we're going to choose Table. This X column where it says X1, that's where we're going to type in all of our X values. And as we already discussed in that problem, the previous problem that we're talking about here, our vertex is at -1, 3. And I need 2 X values above that and 2 X values below that. So if I went down 2 X values from -1, that would bring me to -3. And then I need to make sure I have 5 total, so now I'm going to count up. So I'd have -2, -1, 0, and 1. So there are my 5 X values that we already talked about, and we picked those again for the reason that the vertex was in the middle. Now I'm going to type in my function into the Y column. I'm going to erase what it has there. I'm going to delete Y1, and what we're going to do is type in the function, and we don't have to say y equals, we're just going to say the part that's on the right side of the equation. So that starts with parentheses. Now when I type in x, instead of just x, I have to type in x1 because that's what it's labeled in my x column. In order to do that, you just type x and then the number 1, and it automatically gives you a subscript. And then I'm going to type in +1, close my parentheses. In order to do a square, you press Shift and then the number 6. It's called a caret. It looks like a little up arrow, and that's how you get into the exponent level. So I'm going to put in my 2. Now, in order to type in the last part of my function, which is +3, I have to press the right arrow so that my cursor comes down from the exponent, and then I'll type in my +3. And now I'm done. I already have my X values typed in, and now here are my Y values. And as an added bonus, you can actually see what the graph should look like. So it does plot the points, and that's another good indicator that you're doing things correctly if your graph looks the way you expect that it should. Another thing you might want to check, just to kind of triple check that you have typed everything in correctly, by looking at the equation, we know that the vertex is -1, 3. So you want to make sure that at your vertex X value, your Y value is what you expect, because if it's not, that means you probably typed something in incorrectly. To use the calculator to find the table information, the first thing you need to do is go to Y equals, and you're going to plug in your function. So you have to type it in exactly how it looks on your paper. So parentheses x +1 parentheses squared, and then +3. Now we're going to go to the table. So you'll see up above the graph button, you see written in blue it says table. So we're going to press second graph, and it's going to take us to a table. Now we decided that we needed to start our X values at -3. So you want to arrow up until you can see -3. And then you can look at your Y values, and those are the ones that you want to copy down onto your table of values. Here is how to get a table of values on the TI-30XS calculator. In order to get to the table, we want to go to the table button. And we're going to enter in our function exactly how it's typed on the paper. So parentheses, x, which is this button right here next to the 4, +1, and then parentheses. I can use this square button right here since we're talking about a quadratic function. If you were looking to do any other exponent, you would use this button right above it, where you can type in any exponent, and then +3. Now I'm going to press enter. It's going to ask me where I want to start my table step. I would suggest just keeping everything how it is until you hit OK. And then here's our table of values. Remember that in this problem, our vertex was -1, 3, and I want two numbers above and below that. So here are my numbers. You can't see them all at the exact same time, but you can see them if you scroll up and down. So these y values are the ones that I want to copy down, and you just make sure that you put the correct y values with their corresponding x value.
So I'm going to go through and show you how to get a table of values on the TI-Nspire. So first thing, turn on your calculator and wait for it to load. Once the calculator is turned on, you from the home screen, the little house button, you want to select New Document. If it asks you to save, just say no, unless it's something you really want to save. Then you're going to select a graphs page. And down here in the F1 of X spot, you're going to type in whatever function that you want to get. And we're just going to keep it really simple for this demo. I'm just going to use x squared. So I'm going to type in x squared, hit enter to graph, and here's my graph. Now to get the table, from here you're going to hit menu. And as you can see down here, it says table. You're going to choose split screen table, and you will have your table pop up.
Hi everyone, this is how to set up your table set in your Casio graphing calculator. I have to make this up because I couldn't find one on YouTube. So the first thing you want to do is go into your menu. Make sure that in your graphing menu that you have an equation set in there. So I put this one in. Okay. So to get to the table set, you want to go back to your menu, use your arrow key to get to table, which is right here. Hit execute, and you should get this window here, which has the equation in it that you typed into with your graphing, in your graphing menu. So the first thing you want to make sure of is that this equation is selected, all right? So it is right now. You can see there's a highlight on the equal sign. If you press F1, you notice it's gone. All right, so you want to make sure it's selected if you want to set up a table for it. Then you want to go to table set, which is F5. And this is where you set your values for X, your start and your end values for X. So first start, what I'm going to do is put in 10 and then execute, and I'm going to end at -10. And you can start and end your table wherever you want. And then step here helps you to set your increments. So if I want to go up by 2s, then I'm going to type in 2, execute, and then execute again. It gets us back to this window, and if I want to see the table, then I press F6, and here's our table. So notice that our increments are 2. We go from 10 to 8 to 6 to 4. So the first column are your X coordinates, and the second column are your Y coordinates. You can scroll down by using your down arrow. Okay, and to read it, if X is -8, then Y is 130. If X is -6, then Y is 60. And if I want to go back and rechange my increments, so I go to exit, gets me back to this window. I go back to set, and let's say I want to go up by 1s, so I type in 1, hit execute, execute again, and then I go back to my table, F6, and now you can see that your X coordinates have increments of 1. Okay, and once again, to read it, if X is 4, Y is 70, if X is 5, Y is 104. And that's it. It's as easy as that.
Let's talk first about what our transformations are. If I look at my function, I don't have an A value, so that means I don't have to say anything about the graph having a stretch or a shrink. I see that inside the parentheses, my H value is -2. So that means this graph is actually going to get shifted to the right 2. and then my k value is -1, so that means this graph will be shifted down 1. To start my table, I need to use that h and k value to put the vertex in the middle of my table. So remember that your h value is going to be switched. So instead of -2, it'll be +2, and then my k value will stay as is. The rest of my x values, I'm just going to be counting down 2 more values and up 2 more values. So I'm going to have 1 and 0 if I count down, and then I'm going to have 3 and 4 if I count up. Now at this point, you would be typing this information or this function into your calculator, and you would look at the table of values and zero in on the correct numbers based on the vertex that we discussed. So hopefully you've had a chance to watch the video of the calculator that you're going to be using. And so I am going to copy down the correct y values. And again, you'll notice that symmetric pattern on your y values, which should happen. If it doesn't, was probably a mistake somewhere. So I'm going to put a star here. As we discussed, this is the vertex. That's why we chose to put it in the middle of our table. So I am going to fill that in on in the box on the right. All right, so now I'm going to plot these points. So I have 0, 3, 1, 0, 2, -1, 3, 0, and 4, 3. So here's my parabola. So when we talk about domain, and this is actually going to be true of every single quadratic function, domain is talking about how far left and right the graph would go if you followed it forever and ever. And the answer for every single quadratic is that it would go forever. So our domain is going to be all real numbers. Range, however, is not going to be all real numbers, because while this particular graph goes up forever, it stops. There is a lowest point. It stops going towards -infinity where I drew that blue line. So the blue line happens at when y equals -1. So I know that -1 is going to be the number I use in this inequality. And because my parabola is facing up, that means all my values are going to be -1 or bigger. So I'm going to say that the range is y is greater than or equal to -1. So all of my y values are at least -1. Axis of symmetry, now that I know my vertex, I know that it's going to be x equals, and then it's going to be x equals 2 because that's the x value of my vertex. And again, if you draw in a vertical line at x equals 2, you can see that it cuts my parabola exactly in half. So it's symmetric on both sides. X-intercept and y-intercept, that's something that's kind of new. X-intercepts is asking, where does this graph cross the x-axis? So this is my x-axis, the one that goes horizontally, and I can see that there are 2 points that I'm now making red. Those points are my x-intercepts. And a way that you can tell what those numbers are or what those points are by looking at your table is by looking at the points that have a y value of 0. Anything that has a y value of 0 will be located on the x-axis. So I have 2 points that are x-intercepts, and those are 1, 0 and -1, 0. Y-intercept is basically asking me the same thing, except on the y-axis. So that would be this vertical axis here. And I can see that there is 1 point that crosses through the y-axis. And the reverse of what I was saying about x-intercepts is true of y-intercepts. Before, for a x-intercept, we were looking for where the y is 0. Now if I look at where the x value is 0, that's going to give me my y-intercepts. So you can see it on the graph, and you can also see it in the table. Now end behavior is our last issue here. So I am going to write out the beginning part of our end behavior statements, because I know I'm always going to be giving a statement when x goes to the left and when x goes to the right. So if x is going to -infinity, that's talking about the left side of the graph, and when it goes to +infinity, that's talking about the right side of the graph. So now all I'm going to be focusing in on are the left arrow and the right arrow and whether they're facing up or down. So if I look at my graph on the left side, here's my left arrow, and it looks like this arrow is pointing up. So I know that my y statement is going to be going to positive infinity because the arrow is pointing up. And then similarly, if I go to the right arrow on my graph, this arrow is also pointing up. So that means that my y statement will also go to positive infinity. In this function, there are no shifts. It's not going to get shifted left or right. It's not going to get shifted up or down. The only thing that's different from this function and the parent function is having to do with that 1/2. And this 1/2 is actually your a value. So it's going to affect whether your graph has a stretch or a shrink. And because 1/2 is less than 1, this is going to have a vertical shrink. And what that's basically going to do is it's going to make the graph look wider than the original graph. It's going to make it look like somebody took the graph and like shrunk it down from the top and bottom. So it's going to, the bottom part will just look wider. Okay, so in order to get my vertex, normally I would say you take your h and k value, and that is still true. It's just strange now because we can't actually see the h and the k value. So what that means is that our h and our k values are both 0. And I'm going to rewrite this just so you can see the zeros, just so you know for next time where they come from. So for this function, I could write this as 1/2 times x minus 0 squared plus 0. So those two things, the one that's typed on the page and the one I just wrote, those are exactly equivalent. It's just that when you have zeros, it's unnecessary to write them. But that's where your h and your k value are technically coming from. So I'm going to put that 0, 0 is my vertex, and that's going to help me so that I know when I go to make my table of values, I'm going to know what to type or what my other x values should be. So I'm going to go down to and up to. And then you're going to take your calculator and you're going to type in 1/2 x squared and go to the table of values. Make sure you're finding your vertex on there, and then I'm just going to copy down my y values. Now, one thing that you have to be kind of careful about is that depending on your calculator and depending on how you type it into your calculator, sometimes you're going to be given fractions, and sometimes you're going to be given decimals. When I'm graphing, my personal preference is decimals because I think they're a lot easier to locate on the graph. So I'm writing down both. For both -1 and +1, the y value is 1/2 or 0.5. I prefer to think of it as 0.5. All right, so I'm going to graph these points. So here's -2, 2. -1, 1/2 would be here, 0, 0, 1, 1/2, and then 2, 2. All right, so it's pretty subtle, but if you did graph just the regular parent function on here, just to kind of give you an idea, I'm going to do it in red just so you can see what it would look like. So the red one is the parent function, which is just y equals x squared. And then the purple one you can see is on the outside of that, so it's a little bit wider. All right, domain. As we've discussed a few times with these functions, domain is always going to be all real numbers, because if I followed that purple graph all the way to the left and right, it would never stop getting wider. Range is going to have to be an inequality. This one does have a lowest point, which is at 0. So I know that my inequality will include 0. And then because my graph is facing up, that means 0 is the lowest point. Everything else is bigger than that. So I'm going to use greater than or equal to. Vertex we already discussed. That's 0, 0. Axis of symmetry is always going to be x equals the x value of your vertex. So in this case, that's 0. And again, I could put my axis of symmetry in here, and you would see that it's exactly in the center of my parabola. X-intercepts. Remember we talked about in the last problem, X-intercept happens whenever you have a 0 in your Y column of your table. So that would be this point right here, and that would be the point 0, 0 as my X-intercept. And I only have one this time. Incidentally, your Y-intercept, remember Y-intercept happened when you have a 0 in the X column, happens to be the same point. So the point 0, 0 is both an X-intercept and a Y-intercept because it's on both axes. And then last but not least, end behavior. So I'm going to write out my two X statements as X goes to the left and as X goes to the right. So I'm going to look at my left arrow first. Here's my left arrow, and this purple arrow is pointing up. So that means that my Y statement is going to go towards positive infinity. And then same thing on the right side, this purple arrow is pointing up. So my Y is going to also go towards positive infinity. The transformations of this function, there are actually two of them, and they both have to do with the A value of this function, which is -2. So that tells you two things. The negative tells you that this graph is going to be reflected. So what that means is that instead of our parabola facing up, now it's going to face down. And then the 2 is a vertical stretch. Stretch of 2. So what that's going to do to our graph is it's going to make it narrower than our parent graph. So the last example, our graph was wider because it was a vertical shrink. Now because we have a vertical stretch, our graph will be narrower. All right, our vertex has the same situation going on that the last example had. We don't have an H or a K value, so my vertex is 0, 0. All right, now to find the rest of my X values, I'm just going to count down and up. So I'm going to go to -1 and -2, and then 1 and 2. Now to find the rest of my Y values, you will use whatever calculator that it is you're using. So I'm going to use -8, -2, -2, and -8. And again, we've got that symmetric pattern with our Y values, so we know things are looking pretty good. All right, I'm going to graph these points. So -2, -8 would be here. -1, -2, 0, 0, 1, -2, and then 2, -8. So you can see now that this one is upside down, and it looks like somebody's stretching it out. Like if you pulled the top and the bottom of it and stretched it out, it makes it narrower than our original graph. Domain, as usual, is all real numbers. Even though it's upside down, if you followed that graph forever and ever, it would still continue to get wider and wider on the left and right. The range will still be an inequality, but it's a little bit different. Now that the graph is upside down, I don't have a lowest point anymore. I now have a highest point, which is right here at y equals 0. So I know that I'm going to use 0, but now this time, because all of my values are 0 or smaller, I'm going to say that y is less than or equal to 0. Axis of symmetry, same deal as before. X equals the x value. And so if I put in this vertical line at 0, you would see that it goes right through the middle of my parabola. And then for end behavior, I'm going to I'm going to write in my x statement. So I'm talking about when x is going to the left and when x is going to the right. If I look at the left side of my graph, this arrow is pointing down. So now my y statement is going to be going towards -infinity because my graph is facing down. And then if I look at the right side of my graph, this arrow is also pointing down. So this y statement will also go towards -infinity. And you may have noticed that every single time we've done end behavior so far, that our y statements always match. And that's because in a parabola, both of those arrows are always going to be pointing in the same direction. We are going to talk about families where that's not going to be the case, but in a parabola, you can always count on both of your y values either both being up or down, so positive infinity or negative infinity. All right, last example, and there's a lot going on here. I have a negative in front of my parentheses that tells me that this graph is going to be reflected. So when I graph my points, I should expect that my parabola is going to be upside down. My h and k values tell you shifting. So the h value, remember, we're thinking opposite. So this graph is going to get shifted left 1. And then the k value tells us that it's going to be shifted up 2. So I've got 3 different transformations going on here. Now, as far as my vertex goes, remember we're using our h and our k value. That's always going to be your vertex. I'm going to write that up here just as a reminder, because in the last couple examples it was just 0. So my h value, it looks like 1, but remember we have to take the opposite sign, and then the k value is what it is. So I've got my vertex written in there. The next thing I want to do is fill in my x values. So I'm going to go down 2, and I'm going to go up 2. And then for this last part, you can do it in your head if you'd like. You can also type it into whatever calculator it is that you're using to get the remainder of your y values. So I'm just going to copy them down. So I've got -2, 1, 1, and -2. And again, we've got that symmetric pattern going on, so that's good news. I'm going to fill in my vertex while I'm thinking about it, and now I'm going to plot my points. So -3, -2, -2, 1, -1, 2, 0, 1, and 1, -2. So here's my upside down parabola like we talked about. The domain, again, all real numbers. That's true of every single quadratic we're going to talk about. As long as it's a quadratic function, it's going to keep going left and right forever and ever. For the range, there's a highest point on my parabola, which is right here, and that is at y equals 2. So I know that I'm going to be using y and 2 for my range, and because my parabola is facing down, I know that all my y values will be less than or equal to 2. Axis of symmetry is going to be x equals the x value of my vertex, which is -1. And if I put in that line right here, you would see it cuts through the center of my parabola. And then end behavior, remember we always have 2 statements, as x goes to the left and as x goes to the right. And we talked in the previous example about how both of my y statements are going to match every time I'm talking about something from the quadratic family. And if you look at both the left and right arrows of this parabola, they both face down. So I'm going to use -infinity for both of my y statements.